Welcome back. So, in continuation of the previous part of the presentation on historical background of electrochemistry, now let us move on to see how the electrochemistry is related to energy conversion and storage. So, we have seen in the previous presentation that the current and future topics of electrochemistry in the field of energy conversion and storage includes new and improved batteries and solar energy conversion. These two specific cases are what we are going to see now in this presentation. So, as we all know that now there is more and more importance is given for renewable energy conversion because we want to minimize the uh, CO2 evolution and also the CO2 to convert into useful product or bring down the CO2 emission. So that is where the renewable energy is given more important. So you can convert the renewable energy from solar or wind, tidal or hydro electric power. So from this you can convert these energies, and we need again to store them in a different manner. So mechanical, electrical or chemical or electrochemical energy storage. The system shown here, including the lithium ion batteries, supercapacitors, the redox flow batteries, all of them falls into the category of electrochemical energy storage. So before going to the storage part, let us just focus on the solar energy conversion where the electrochemistry becomes more and more important in this field. So let us see an important conversation between Thomas Alva Edison with Henry Ford in 1931. So, in which Alva Edison was mentioning to Henry Ford that I would put my money on the sun and solar energy. What a source of power! So, I hope we don't have to wait until oil and coal run out before we tackle that. So that shows the importance of solar energy. So even it was thought long back. So why not we convert the solar energy into useful energy? So now we'll ask other questions like why solar energy? Because as we all know that solar energy is clean and it's abundant, so and it's economical, so it's available freely. And this can be only captured and converted into useful form. As we all know, energy can neither be created nor destroyed, but it can be converted from one form to another form. In that way, the solar energy can be converted into thermal or it can be do to electricity through photovoltaic cells or photoelectrochemical cells. And the photovoltaic cells, whatever we are using the silicon solar cells, and currently the lab scale the efficiency is achieved is 47%, whereas there is the other way of solar cell which has come as a more economic way compared to the silicon, which is a dye sensitized solar cell where the efficiency is only 14%. The other types of solar cells evolved recent times, including organic solar cells with 17% efficiency, and more recently the perovskite solar cells, which started with the efficiency of 14%. Now it has reached up to 27 percentage of efficiency. So again here, so how this solar energy can be converted includes the photon energy can directly be converted into electrical energy using the semiconductor diodes like silicon solar cells or photovoltaic cells. So it can also convert the light into chemical energy like photosynthesis, what plants or natural plants does. So converting the CO2 into carbohydrates. So similar photosynthetic chemical conversion can be converted, or we can use photoelectrochemical systems to store or convert the solar energy into useful chemical forms. Similarly, the thermal energy can be converted from the light to thermal energy. So that again, once again, can be transferred to electricity through thermoelectric devices, or this can be coupled with the mechanical energy can convert to a thermal engines. So in other way, if you look at a simplest picture, so the light can be converted directly to electricity using a PN junction of semiconductors, which support photovoltaic solar cells. Or if you take this light, if you shine on a semiconductor, so which is kept in a liquid, it can be simply water. So then it can split the water into hydrogen and oxygen, or we can also convert into a fuel like CO2 to sugar, carbohydrate, what plants does the photosynthesis. So this can be also been done in a laboratory by using similar the photoelectrochemical concepts. So that's going to be more useful way of eliminating CO2 or converting CO2 into another useful product. So photoelectrochemical water splitting, where the electrochemistry came into picture, is very useful one. It was in 1972 when Fukushima and Honda they demonstrated the photoelectrochemical splitting of water by using a titanium dioxide semiconductor. So when they shine light with energy more than 3 electron less than 3 electron volt, which is a band gap of this TiO2. So these photo excited electrons they can be sent to the external circuit if you apply a bias. So these electrons can reduce the protons available from the water oxidation to hydrogen gas or the counter electrode which was used as a platinum. So these valence band holes, they oxidize the water into oxygen and they split into protons. So that's reduced here. So this is by this way the water can be split into hydrogen and oxygen separately using such a setup. So with a titanium foil, you can also oxidize them on one side to titanium oxide. So then you can have a membrane so that you can get the hydrogen and oxygen individually. So the process happens can be explained here. The first step is the excitation of the semiconductor by absorbing light. So the excited electrons, which goes through the conduction band and through the external circuit, reach the counter electrode, and the photo generated holes they just oxidize. So suppose you do this in a alkaline condition, so you have a OH minus, so that can be converted into water. So then this hydrogen can be evolved at the counter electrode. So again here, once the Fukushima Honda cell has been started, there is a lot of research has been done to understand the semiconductor electrolyte interface. As mentioned in the history of electrochemistry, Heinz Gerischer so has made a lot of contributions to this. And if you look at a semiconductor, so when they are before equilibrium and you keep the semiconductor in an electrolyte, so there is a Fermi energy of a semiconductor, and this is the conduction band level and the valence band energy level. So once you keep, so this is the redox level in the electrolyte. For example, here the hydrogen reduction potential. So in the dark, there is exists a equilibrium is established, in which case the electrons are transferred from the semiconductor to the electrolyte, so that there is a charge depletion that creates a band bending situation. But once the light is shown on this semiconductor, again the band shifts back. So then the difference between the Fermi energy of the semiconductor to the redox level of this electrolyte produces the open circuit voltage. So for this process to happen, the valence and conduction band levels should be suitable. For example, if you are taking with the water splitting to produce hydrogen, the conduction band level or Fermi energy of the semiconductor should have a potential which is more negative than the hydrogen reduction potential, that is zero electron in the standard hydrogen electrode potential. So there has been various semiconductors have been looked upon, so like gallium arsenide, gallium phosphide, or cadmium sulfide, zinc oxide, depending on their conduction band level or Fermi level with reference to the hydrogen reduction potential. So some of them can be better materials, even it doesn't require any applied bias to split the water into hydrogen. However, their stabilities, that means most of them undergo a photocorrosion process, they dissolve. For example, cadmium sulfide, the cadmium ions dissolve into the solution. So there are other ways to protect this photocorrosion process by having a core shell structure of the semiconductors, so that you can improve the properties or stability of these semiconductors for their application. So similarly, the CO2 reduction into methanol can also, on other valuable products, can also be done using such photoelectrochemical cells. In one example I have shown here includes if you have a cobalt phosphate, and alpha ion oxide, which is available everywhere. So this material, so once you shine light, so this cobalt phosphide sensitizes this, and these electrons, again you have another semiconductor, bismuth ferrite, so that gets excited with the electron, so that is transferred to, there is enzymes, so that can reduce the CO2 into methanol. So this process happens. So if you example typically look at the cell, so the cobalt phosphide with the alpha ion oxide acts as this electrode, and this electron goes to the poled bismuth ferrite. Bismuth ferrite is known as a multiferrite material. So once you pole that, there can be efficient or effective charge carrier separation. So through which the NADH comes into picture. So there is a redox process, and this facilitates the CO2 conversion into methanol. So similarly, it can be converted into other products as well. So that this will be going to be a useful way of eliminating the CO2 from the environment, or to convert it into a useful product. The other way of converting the solar energy is directly if you take a photovoltaic cell, it's a PN junction of a semiconductor. So we are familiar with the silicon solar panels installed everywhere. So we can see the configuration. So in this case, instead of silicon, you can also use copper, indium, gallium diselenide to improve the light absorption, or gallium phosphide, the other semiconductors. So the architecture looks like this. So you have a glass panel on which you have the finger type metal electrodes for the charge collection, and this glass coated with the transparent conducting layers, for example the zinc oxide with the aluminum, or then there is a buffer layer, then you have the electrode deposited copper, indium, gallium diselenide, so that acts as the light absorber, and then that is a semiconductor. So then there is a back conduct of molybdenum and again a glass. So this is a typical the solar panel which exists here. But there was an alternative here for this kind of method, so it needs a lot of processing to make. There was a simple method reported as a different type of solar cell, which was known as dye sensitized solar cell. So it was reported in 1991 by Professor Gratzel from EPFL Switzerland. So this was a low-cost, high-efficiency solar cell based on dye-sensitized colloidal TiO2 film, in which they used just a medium purity materials through low-cost process. So that exhibits a commercially realistic energy conversion system. So here in this case, TiO2, which is transparent to visible light, so this can be sensitized by anchoring a dye. So dye can be a ruthenium complex. So that absorbs the light and sensitizes the TiO2. That electron goes to the counter electrode, so completing the circuit. So this is the IV curve of this cell developed here, and we can look at the open circuit voltage, which is 0.72 volts, and the short circuit current density is current is 3.5 milliamps. So for this, the current density is 20.53 milliampere per centimeter square. With this cell, the efficiency obtained was 10.4%. So in the case of DSSC, if you want to improve, so we need to work about how to improve the open circuit voltage as well as the short circuit current density, and there is a lot of uh, trade-off between these two. If you improve the open circuit voltage, you may not achieve the high short circuit current density. So there are ways how to enhance. So there are different reports have been available, and people are still working to improve these parameters to enhance the efficiency of a DSSC cell. So if you look at deeper the DSSC cell, so it has a conducting glass, transparent conducting glass, on which this metal oxide, for example titanium dioxide, is coated here as a mesoporous film, and it was soaked in a dye solution, and these dye molecules anchor on the surface of this metal oxide, and we have the electrolyte, and then we have a counter electrode. Most of the cases it is platinum, and now that it can be replaced with the carbon based electrode like carbon nanotubes or the graphene or other types of materials. So once the light is absorbed by the dye molecule excites, and this excited electron is transferred to the conduction band of titanium dioxide, through which it goes to the external circuit to the counter electrode. So this dye molecule, once it transfers the electron which is oxidized, And to regenerate this dye molecule, there is an electrolyte. So these electrolytes gets oxidized here by reducing the dye. So this electrolyte gets reduced at the counter electrode. So this process becomes a continuous process. However, there are other drawbacks of this. There is a recombination of this excited electron, which can combine with the electrolyte, which can also penetrate through the mesoporous layers of this metal oxide, or this electron can come back to the HOMO level of the dye. So for this DSSC to happen, there should be alignment of the energy levels. For example, to regenerate the dye, so the HOMO level of the dye should be much positive potential compared to the redox potential of electrolyte. That means the electrolyte should have more reducing power to reduce the oxidized dye molecule. And again, the conduction band level of titanium dioxide should be just below the LUMO level of the dye so that the electron transfer happens. So the time scale at which this process happens, the electron injection happens at the picoseconds, and the dye regeneration happens in the nanoseconds, and some of the recombination process happens in the millisecond. So these recombination processes should be minimized. So of course, you can have certain blocking layers through which you can minimize the penetration of electrolyte or this back electron transfer from the conduction band of titanium dioxide to the electrolyte, or this also blocking layer can enhance the fast transfer of the electron. If you have a thin layer of such oxides, so the fast electron transfer can happen to the external circuit. So again, to change the light absorbing power, so we can use a different dye molecules based on the ruthenium complex. For example, here the L is the 2,2' bipyridyl 4,4' dicarboxylic acid. So this can also be changed to terpyridyl groups so that the optical absorption spectrum of this and the color of the dye can change, so that you can tune. So in the solar spectrum, so you can change the wavelength of optical absorption of these dyes so that each one will perform its best efficiency at a different wavelengths of the operation. So again, the electrochemical technique, impedance technique comes into picture where you can understand these processes happening in a dye-sensitive solar cell. For example, the dye transfers the electron. If you have a sintered spherical particles of the semiconducting oxides, the electron has to travel through several particles to reach the conducting glass plate. On the other hand, if there is a nanotube array of these semiconducting oxides, so for the resistance for this electron transfer can be minimized, and all these processes can be modeled using the equivalent circuits. With then we can measure the impedance of this, and we can fit the uh, data of these cells under operation. So if you look at this, so the whatever happening at the counter electrode, that is the reduction of the electrolyte, so that can happen. If you look at the Nyquist plot at high frequency, this is the semicircle that represents this, and this middle semicircle represents the metal oxide and dye and electrolyte interface, and the electrolyte charge transfer and its resistance, everything can be modeled using this semicircle that comes in the Nyquist plot. So using this, we can also obtain the lifetime of the electrons, and we can characterize different materials, whether how to modify a material to improve their properties, whether you want to minimize the resistance to improve the better charge transport properties. So everything can be understood using this kind of electrochemical techniques. So this is the National Renewable Energy Laboratory in the USA. So they give certification for various types of solar cells. So whatever made globally. So this has been updated every year. So now we can see that if you look at the dye-sensitive solar cell, which was started here in the 1991 with 10.4% efficiency. So even it has reached only about 14% of efficiency till 2012 or 2013. On the other hand, if you look at perovskite solar cell, which started with 2012, so which started with the efficiency of about 14%, now it has reached to 27% of efficiency. Again, among the various photovoltaic cells like silicons, so there are single crystalline, polycrystalline, and tandem cells. So different varieties of the solar cells are available on the photovoltaic side. So then the maximum efficiency obtained using this kind of silicon solar cells, which four junction cells. So the current efficiency has reached 47 percentage. So that's the maximum tested efficiency available today. Having converted the solar energy, now we want to look at not only solar energy, the different types of renewable energy from other sources. So we need to look at the energy storage systems. So energy storage systems, so electrical energy storage. So how to store? So they have become the holy grail of electric utility industry. So mechanical or electrical, chemical or electrochemical means are available for the electrochemical energy storage technologies. For mechanical, you can have a compressed air or pumped hydro power so that you can store the energy. And similarly, we have electrochemical energy storage system that again can have a different types like supercapacitors or lithium ion batteries or lead acid batteries or the redox flow batteries. The advantages of the electrochemical energy storage systems are their pollution free operation, long cycle life. They can be having a flexible power and energy characteristics depending on their applications, and low maintenance. So if you compare again among the electrochemical energy storage systems, so we have batteries, fuel cells, redox flow batteries, and supercapacitors. So the energy storage mechanisms are different in each category. So in batteries, the energy is stored within the electrode structure through charge transfer reactions, whereas in fuel cells, the energy is stored in the reactants, for example, hydrogen and oxygen, which when combined to form water, so that releases the energy. So these are fed externally to the cell. Similarly, in the redox flow batteries, the energy is stored in the redox species that are continuously circulating through the cell. In supercapacitors, the mechanism is capacity process arising from an electrochemical double layer at the electrode electrolyte interface. The examples for batteries include sodium sulfur or lithium ion or sodium ion batteries, and similarly, fuel cells have different categories: alkaline, phosphoric acid, or methanol, or proton exchange membrane types. And similarly, redox flow batteries include zinc chloride, chlorine or iron chromium, zinc bromine, vanadium bromine, or all vanadium systems. Supercapacitors can have the materials that form supercapacitor can be of various types of carbons, ruthenium oxide, manganese oxide, and various conducting polymers and their composites. So if you look at the sodium sulfur batteries, the molten sodium is kept here in the sodium beta alumina, which also serves as the electrolyte. So through which the sodium can, during the discharge, it diffuses through the sulfur, form sodium sulfide. Again, on the charge, the process reverses. In the case of lithium ion battery, the cathode materials are layered compounds containing lithium. So during the charge, these lithium ions moves towards the anode, which is normally the graphite. So here the lithium ions are stored. During the discharge, the lithium ion again moves back to the cathode. So the electron comes to the external circuit. A similar way, so there is a, instead of this lithium ion battery, there is a lithium air cell, so which has more energy density compared to lithium ion batteries. In this case, the lithium ion goes through the electrolyte, and there is a composite electrode made of carbon and the redox catalyst. So the oxygen gets here reduced, and once the lithium goes, it forms Li2O2, and similarly during the charge, it reverses the process. In the case of redox flow batteries, so we have the electrolytes, the anolytes and catholites. For example, in the case of all vanadium flow batteries, so we have vanadium 2 plus 3 plus couples in the anolyte, and the catholyte has vanadium 4 plus 5 plus. So these electrolytes are continuously pumped through this, and then this redox process happens through which we can store the energy. So again, as our energy demands are increasing, so and we are having portable energy, high energy demands. So it was found that lithium cobalt oxide, which was first discovered or made possible for lithium battery in 1987, and it was implemented commercially in 1991. Then came the lithium iron phosphate in 1997, and then the lithium nickel cobalt manganese oxides and LiFePO4 they are implemented in 2007. But again, how to store for large energy storage or electric automotive vehicles are also integrated system. So there needs to be a future battery systems, either it can be a single or coupled with other technologies as well. So if you look at the energy density and power density, So batteries, lithium-ion batteries are here, whereas compared lithium lead acid, so they have higher power density as well as energy density. But capacitors comes with a high power density compared to lithium-ion batteries. And then we have a lithium air which has more energy density compared to lithium energy. So these can occupy the future technologies. That's a beyond lithium-ion batteries. So how to go with the so the years from 91 to 2000 has seen the engineering aspects of these rechargeable batteries, and in between 2005 and future they look at alternative new materials as cathodes and anodes, and then beyond lithium ion. So for example, sodium ion or the lithium air and other lithium sulfur technologies are going to be there in the future. So the advent of lithium-ion batteries. So this is how the Sony Corporation made. So using a lithium cobalt oxide as cathode, from which lithium can be removed to go to the anode on the graphite. So this can be get back to the cathode during the discharge process. So there are variety of cathode materials have been evolved. So for example, in the ordered rock salt structures, so LiMO2, but here the problem is only 0.5 lithium can be removed per metal atom, whereas in the spinels you can get higher energy, 4 volts. So, but this structure can be robust, so they can hold. But again, there are issues with the until distortion of manganese 3 plus at 3 volts, and the solubility problems at high potential comes here. And the olivines with the LiFePO4 or LiMnPO4, they show a very stable structure. For example, LiFePO4, if you remove lithium, it converts to FePO4, which is also stable, and it goes back to LiFePO4 during discharge. So, how the problem with this is the poor electronic and lithium-ion conductivity that can be improved by coating with the carbon materials. So there are a lot of opportunities available to develop various cathode materials. Similarly, on the anode side, so carbon, that's a graphite has been used as a more stable anode for the lithium-ion batteries. So other materials like silicon or tin or cobalt tin alloys or intermetallic compounds like copper tin, everything has been established. The problem comes, for example, if you take a silicon or tin, so the volume expansion, so that leads to the short circuit of the cell. So by having a carbon coating, so we can also minimize that, so that carbon can have like a buffer layer. And similarly, the metal oxide, for example, the spinel lithium titanium oxide shows a better performance with stable even in the nanoparticle form. So it shows 1.5 volts versus lithium as an anode material. So these are the energetics that needs to be matched. If you have an anode, the Fermi energy of these compared to the electrolyte or separator, and the cathode levels should be, the Fermi energy should be here. So the cathode materials, if you look at so far based on the lithium metal redox potential, so we can see the maximum voltage so far obtained using the lithium cobalt oxide for instead of lithium manganese oxides. So the theoretical and practical properties of batteries, if we compare with lead acid, so the theoretical capacity is only 83 ampere hour per kilogram, whereas the lithium ion, if you take for example LiCO2 for removal of lithium X is 0.6, you can get a 95 ampere hour per kilogram, as well as the practical energy density obtained by lithium ion batteries much higher than the lead acid batteries. So for the people who work on the lithium-ion battery research, so it was the happiest moments last year because the Nobel Prize in Chemistry for 2019 was awarded for the development of lithium-ion batteries. And Professor John B. Goodenough and Stanley Whittingham and Akira Yoshino. So the contribution was they created the right conditions for a wireless and fossil-free society. That's how they served the mankind. So it was Michael Stanley Whittingham, so who in the year 1976 showed that if you take a lithium as an anode and the titanium disulfide is having a layered structure, so through which you can do a intercalation, deintercalation, that's insertion and deinsertion of lithium, so that you can make these lithium-ion batteries. So this one operates at 2 volts. Then Professor Goodenough replace this kind of sulfides. So if you make an oxide as your cathode, so you can go still higher voltage. So it was a lithium cobalt oxide that he used in the year 1980. So he could demonstrate 4 volts. But in both the case, the anodes are lithium. So then there is a safety issue comes into picture. There some of the batteries have exploded. So it was Akira Yoshino who took this lithium cobalt oxide and then he used a petroleum coke. So when he was trying with various carbons, so petroleum coke showed a better performance. So he demonstrated the 4-volt batteries with a safely without any problem. So this was in 1986, and the first commercial lithium-ion battery was started in 1991, and it is Professor John B. Goodenough who obtained this Nobel Prize at the age of 97 years. So he is the oldest Nobel laureate in the history of Nobel Prize. So again, if you look at this Ragon plot, so the batteries have the energy density is higher, but power density is low. So, but the capacitors, which has high power density but low energy density, certain application needs very high power density. So, for which for purpose, so we can go for a capacitors. So, why electrochemical capacitors? Because the energy storage can be done in batteries, but lithium-ion batteries, the charging and discharge, that's the power delivery and power uptake, can be a slow process, whereas electrochemical capacitors, this can happen very fast. So electrochemical capacitors, there is a double layer capacitors or pseudo capacitors, depending on how the charge storage happens. So most of the carbon materials, they store the charge at the double layers, whereas if there is a redox process happens at the material, for example, manganese oxide or ruthenium oxide, the capacitance is much higher than the EDLC. So they called as a pseudo capacitors or super capacitors. So these capacitors are useful for portable electronic or hybrid electric vehicles. And again, the challenge is developing new materials. So understanding the electrochemical interface at the nanoscale. So they are important in making different materials and improve the performance of these materials. So again, comparison of lithium battery and electrochemical capacitors. So the charging time takes 3 to 5 minutes, for example. So here it's 1 second. So discharge time again it's fast, it's same. So the cycle life. So capacitors have more than 5 lakh hours, but whereas it is only up to 5,000. So at 1C rate, and similarly energy density is higher for batteries, lithium-ion batteries, whereas capacitors low, but it is otherwise the power density is very high for the capacitors. So this is how. So for example, if you look at this one, so we know the better how appreciate what is the charging process and discharging process of supercapacitors, which is faster and rapid than the battery charging and discharging process, so which are very slow. But there is applications, so we can use them as a combination. So wherever you need more power or instant power, we can use the capacitors. So again, the properties, if you look at battery and capacitors, the storage mechanism is chemical here. The lithium ion goes into the lattice of the cathodes or anodes. So whereas here it is a physical, the double layers or at the surface of your electrode material. So power is limited by the electrochemical reaction kinetics and active material conductivity or mass transport in the batteries. Whereas in the capacitors, so it is limited, the power is limited by the electrolyte conductivity in separator on electrode pores. And similarly, the energy limitation comes from the electrode mass in the case of batteries, whereas it is the electrode surface area that controls. So if you want to improve the surface area of the electrode material, so we can increase the charge storage, that is the capacitance of a capacitor. So similarly, output voltage can be controlled by approximately it's constant in the batteries, whereas it is having a sloping value. So both state of charging known precisely here. The charge rate is slow. It depends on the reaction kinetics, the intercalation or deintercalation processes, and mass transport, whereas it is very high in the capacitors and it is same as the discharge rate. So cycle life is limited in the batteries depending on mechanical stability and chemical reversibility of the electrode materials for the insertion and deinsertion of the lithium ion. Whereas in the capacitors, the cycle life is limited by any side reaction. So if they are going to be affecting the performance, so then the cycle life is limited here. So life limitation again it depends on the thermodynamic stability in the batteries, whereas the side reaction that controls the life limitation in the capacitor. So if you look at the materials that have been used for electrochemical supercapacitors, it was a carbon, so various forms like activated carbons or carbon aerogels or the nanotubes or graphene. So here we can get about a 300 farad per gram as specific capacity, Whereas then it came the polymers, like conducting polymers or different types of polymers, where you can get around 300 farad per gram. In the case of metal oxides, again, manganese oxide itself can, with the different modifications, can show up to 800 farad per gram. And the ruthenium oxide, which shows about 1200 farad per gram, with combined with other types of polymers, or this can also combine with other oxides. So these two are known as the pseudo capacitors, but the cost of ruthenium oxide is more. So to make the composites, so that we can minimize the cost, also we can explore by making composites or looking at improving the properties of manganese oxides. So for example, here it is shown from the activated carbons to different types of metal oxides like ruthenium oxides and manganese oxides. So the capacitance has increased up to 1200 farad per gram. Similarly, the voltage can be improved. So if you are using aqueous electrolyte, the voltage is limited to 1.2 volt or even less. But if you go with the organic electrolytes, so your voltage can be increased. Or you can also use ionic liquids, or you can make asymmetric configurations of the capacitor materials so that you can increase the operating voltage of the capacitors. So well, so we have seen the basics of electrochemistry, how it originates. So we know now that electrochemistry plays a vital role in solving major issues faced by the humankind, whether it can be related to energy, environmental, biology, medicine, or corrosion protection, etc. So electrochemistry can provide solutions. So similarly, we have seen here the electrochemical energy storage devices having advantages than the other types. So they can be easy and simple and robust. So there are more opportunities for improving the materials properties and designing new technologies to meet the energy demands of requirements of the society and the future energy demands as well. So that's why we need to develop more and more material. And CSIR-CECRI, being a hub of electrochemical technologies, provides a lot of opportunities for the youngsters or the students or researchers and the scientists, more opportunities to tackle the problems associated with energy or environmental or medicine or corrosion, so and solutions for these problems also. So thank you for your kind attention.